This next video is on derivatives and differentiability behavior. So the derivative will exist at a point as long as the curve is smooth with no sharp turns and no vertical tangent lines. If the derivative exists at a point, it can be said that function is differentiable at that point. Sharp turns commonly occur on absolute value functions. Okay, so if we do a quick sketch of an absolute value function, let's just use the parent function where that it's a linear function, but we are applying the absolute value transformation to it, okay? So at this point, because we have a sharp turn here, that means at x equals 0, that point is considered non-differentiable. And we already talked about this in class, and we will talk about this later in the packet, but because if we apply the limit from the left side and the right side, not the limit, I'm sorry. If we look at the slope from the left side and the slope from the right side, they are not the same. In fact, they are very different, all right? One slope is positive and the other is negative, okay? And we can evaluate this analytically as well. So if we take, let's call it g of x, and it's the absolute value of x, okay? Absolute values, they reference back to distance. We're looking at the distance from, could be the center or a certain point. Okay, so however far I travel to the left or up or down, I also want to travel that same distance in the opposite direction. Okay, so in this case, if I have x, I can think of plus or minus x. Okay, so if I'm starting at a point and I take the absolute value, I will travel this distance x, and then I will travel this distance x. But this one's in the positive direction, this one is in the negative direction. So now that we have two separate functions, we can rewrite them as a piecewise function. We can have a piece that represents the positive x, and then another piece that represents the negative x. However, within these piecewise functions, you also need to include their domain restrictions. So based on the graph to the left, positive x will go from 4 when x is greater than 0, and then we can say for the negative x, it'll be when x is less than or equal to 0. And then for the equal to, you can include it with either one, but do not include it with both. However, it does need to be included somewhere because this function is continuous. Now, if we take this a step further, if we think of g prime of x, we can see that the slope for the positive x is going to be positive 1, and the slope for the negative x is negative 1. Now, for the positive one, the domain will be x is greater than 0. And then for the negative one, it will be x is strictly less than 0. Because it is non-differentiable at x equals 0 should not be included anywhere in the first derivative, okay? So if we think about x equals 1, the slope is going to be positive on the right side, and it's negative on the left side, which means it is non-differentiable. Okay. All right, so let's look at this example down here. Go ahead and just so it's not squeaking. All right, so we have a function -2 absolute value of x minus 3 plus 7. We want to identify where it's positive, 0, and negative. And then we also want to include the domain values with that. So again, the solution's already provided, but we can go ahead and discuss what we're looking at. So if we start to the left, the function is increasing, and we can see the slope is positive. Now, for these absolute value functions, we know the exact value of the slope. It's given as part of the function, all right? So on this side, m is equal to 2, okay? Now, on the other side, oh, I should have used red for that. Oopsie. Now, for the other, no, because it's positive, so I'll use red for this side, okay? The slope is negative, and we actually know what the slope is. It's -2, okay? So the slope is positive, or f prime of x is positive on -∞ to 3, and then f prime is negative from 3 to infinity. Now, this is another case where you cannot include it within this domain, okay? Due to it being non-differentiable at x equals 3, you cannot include it with either of those domains. It doesn't fit the realm of, oh, we can include it or not include it, all right? So it is undefined. F prime of x is undefined at x equals 3. Now, f of x is defined, right? It is a continuous function. There's an output at 3. However, the slope at the point of 3 does not exist, all right? So it's not differentiable at x equals 3 due to that sharp turn. Oh, we'll talk about it on the next page. Example 2, same thing. So we have x squared minus 4. Now think about what x squared minus 4 looks like without the absolute value. It's going to have a vertex at 0, 4. Yes, sorry, 0, negative 4. Okay. So when we add this, or I'm sorry, when we apply this absolute value transformation, remember it takes all of the y values and it's going to reflect them above the x-axis, okay? So that's going to shift our vertex to go from 0, negative 4 to be at 0, positive 4, okay? And then the tail ends that are above the x-axis will still continue on like they did before. So again, the solutions are provided, but let's talk through them. So if we start from the left side, the function is decreasing, okay? I don't know the slope, but I do know that f prime of x is going to be negative from negative 2 to 0, okay? Not negative 2 to 0. Yeah, I'm sorry, negative infinity to negative 2. I was looking at this, but thinking, yeah. So it's going to be negative infinity to negative 2. And that negative 2 cannot be included, right? Because at negative 2, this is non-differentiable, okay? So therefore, it cannot be included, okay? And then after that, from negative 2 to 0, the function is increasing, therefore the slope is positive, okay? So it's positive from negative 2 to 0. And then at 0, 4, we have a smooth curve, and the slope of the tangent line at that point is going to be 0. Therefore, f prime of 0 is equal to 0. After that maximum, the function decreases, which means the slope is negative. So f prime of x is negative on 0 to 2. And then finally, the last tail end is going to be increasing, so the slope is positive from 2 to infinity. And then we also have that non-differentiable point at x equals 2. All right, so differentiability and continuity. We have been talking about this somewhat already. What all of these functions have in common is that they are continuous, all right? Absolute value functions, continuous, if they don't have a break, all right? But the two absolute value functions that we were looking at are in fact continuous, yet they do have points where they are non-differentiable, okay? So if we take a look at the greatest integer function, aka the step function, okay? There are an infinite number of breaks here. It is not continuous, all right? So at those moments where it's not continuous, if you think about what we talked about with the slopes from approaching either side of a point, when they are not the same, then that's going to cause a point to be non-differentiable, okay? So it's not continuous and non-differentiable. Because if I ask, okay, what is f prime of 0? Well, we have a value for 0. It's going to be 0. But if I look at the slope from either side, it is also 0, but it's not continuous, all right? If a function is not continuous at a point, it is not going to be differentiable, right? In order for differentiability to occur, the function has to be continuous at that point, okay? Now, the same cannot be said for the opposite. We have a continuous function, the absolute value function, so it is continuous. But if we look at that break, the rate of change, it's different on both sides, all right? So it's continuous, but it's non-differentiable. And then we also have our cubed root function. And you've seen the cubed root function since Algebra 2, I believe, but we don't really talk about what's happening at 0. This is actually a vertical tangent line. So the slope of the tangent line at x equals 0 is actually infinite because it's vertical, all right? Which means we don't have an actual scalar value for that slope, therefore it is non-differentiable at x equals 0. So yes, x cubed is continuous, but it's non-differentiable because of that tangent, or that vertical tangent. Now, I did not mention this in class, but I will bring it up tomorrow, or sorry, I don't know when you're watching this video. Another scenario where it's non-differentiable is when you have what's called a cusp, okay? So at this point here, we'll call it 1. We will see functions where they have a cusp. They are continuous, but at the moment or the value where the cusp occurs, it is non-differentiable. And it's for the same reason for the absolute value function. Okay, I couldn't fit non-differentiable, but that's what it says. All right, so a couple more examples where the function's derivative is 0, and we want to identify, so for each function, identify where the function's derivative is positive, where the function's derivative is 0, and where the function's derivative is negative. All right, so we have two absolute value functions. So already noting, we're going to have non-differentiable points included in these, okay? So for 5, sorry, I had to move places because my roommate just got home. So if we take a look at this, the point where it's going to break is going to be -1 and -2, okay? So we'll put that here, and it's going to open up, okay? So this is point -1, -2. Sorry, -1, -2. Okay, so we actually know the value for the derivatives for all of these points because of the slope here, okay? On the left side, we are decreasing, which means the slopes will be negative. And then on the right side, we are increasing, which means your slope will be positive. And then at x equals -1, that point there is non-differentiable. All right, so f prime of x is less than 0 on -∞ to -1. And then f prime, we can go ahead and specify that it's -1. F prime of -1 is non-differentiable. Or you can say f prime of x at x equals -1 is non-differentiable, but this saves a little bit of time. And then we have f prime of x is greater than 0 on -1 to infinity. All right, this next one, we have a parabola, and we're applying an absolute value. So if we draw a sketch of this, think about what's happening with this parabola. It's 25 minus x squared. The negative is in front of the x squared, which means the parabola, the original parabola, will be facing downwards, okay? So that means our vertex is going to be at 25. All right, so if it's facing downward, it's going to be hitting the x-axis, and then due to the absolute value transformation, the tail ends are going to bounce up. Now, hopefully you recall how to figure out what points these are, because you need them, because you have to mark the non-differentiable points. This should be -5 and +5. So if you have 25 minus x squared equal to 0, 25 equals x squared, you end up with plus or minus 5 is equal to x, and that's going to be your x-intercepts, okay? So now from here, we can go ahead and write our statements out. So from the left side, it is decreasing. The function is decreasing. Therefore, the slope is negative. So f prime of x is negative. And I know I keep switching. I'm switching on purpose. This is acceptable. This is also acceptable, okay? So I keep switching between answers that will be acceptable for this course and for AP Classroom, or College Board, I'm sorry. So f prime of x is negative on, we'll say -∞ to -5, okay? At -5, this is non-differentiable. So f prime there's multiple, so I'm going to say f prime of x is non-differentiable at x equals, and I see another one at positive 5, so we'll say plus or minus 5. Or you can say f prime of negative 5 and f prime of 5 are non-differentiable. Either one will work, okay? After negative 5, we are increasing. Therefore, the slope is positive. So we have f prime of x is positive on negative 5 to 0. And then at 0, we have the slope of the tangent line is going to be 0. So we can say f prime of 0 is equal to 0. After the maximum, we are decreasing. Therefore, the slope is negative. So we can add a union to our first statement, union 0 to 5. And then after the non-differentiable point at x equals 5, function is increasing. And it's increasing from 5 to infinity, so we can add that to our positive statement. All right, hope that's helpful. The next video will be on limits.